Chapter 6.1, further momentum. First we will see energy in collisions. By the end of this section you should be able to explain the difference between elastic and inelastic collisions. Okay, so we will learn what an elastic collision is. In an elastic collision the kinetic energy is conserved. That means the total kinetic energy before collision is equal to total kinetic energy after collision. Then if it's inelastic, it's not conserved. So we will learn the details afterwards. Make calculations based on the conservation of linear momentum to determine energy changes in collisions. Now momentum, linear momentum. Okay, so energy is always conserved. We have learned the law of conservation of energy. Derive and use equations for the kinetic energy of a non-relativistic particle. We will see the details afterwards. Okay, so you can see over here what happens is after collision the vehicle crumples. Therefore what is happening is the kinetic energy converts to another form. Now this gets deformed. So because it gets crumpled, the kinetic energy is converted to other forms like heat. As a result, the kinetic energy is not conserved. So the total kinetic energy before is not equal to the total kinetic energy after. Therefore it's an inelastic collision. Alright, so here is an example of an elastic collision. We have here a picture of the Newton's cradle. What happens here is, in reality there is a decrease in the kinetic energy, but it is very little. So this bob or this ball here will strike this, and then the energy is transferred all the way to this side, and this bob here or this sphere will move upwards, and this process continues. So as soon as this hits this sphere over here will start moving up. It will move up a certain height and then fall back down. Afterwards when it hits this again, the force is transmitted, and then what happens, this will go back up and the process continues. Okay, so here is an example where the kinetic energy is conserved, but it is finally the kinetic energy will decrease, but the kinetic energy loss is very little here. Always in any example the momentum is conserved. Total momentum before is equal to total momentum after in any case, but kinetic energy may or may not be conserved. However, the momentum is always conserved. Let's look at another example. A collision in which total kinetic energy is not conserved is an inelastic collision. The word here total is important because it's the kinetic energy of all the bodies before collision and the kinetic energies of all the bodies after collision. That's why we say it's the total kinetic energy. Now let's consider this example here. We have learned the formula for momentum. Momentum equals mass times velocity. So the initial momentum of this is 300 times 5, the mass times the initial velocity, and the momentum of this before collision is 300 times 1. Then after collision it's 300 times 2 for this one and 300 times 4 for this one. So you can see that here they have shown it in terms of kinetic energy. Now we can also see the momentum. Total momentum before should be equal to total momentum after, always. Okay, so if you multiply this and add it to the product of this, you will see that the total of this is equal to the total of this. And let's find the kinetic energy. We have learnt only one formula for kinetic energy, that is half mv squared. So if you have a kinetic energy question, most probably you will have to use only that one equation if you want to find the kinetic energy. So here we have kinetic energy is half mv squared. Now we are using u here because this is the initial velocity. So this is the kinetic energy of this, and then again we can use this formula to find the kinetic energy of this one. So half m u squared. Okay, so this is for this, and here the speed is 5, so we get this. Now total kinetic energy before collision is 3900. Similarly, we can find the kinetic energy after collision. We know the mass of this, we know the velocity. So using kinetic energy equals half mv squared, we can find the kinetic energy of each of these before and after collision. So here we find it after collision. Now you can see after collision the kinetic energy is 3000 joules. Before collision it is 3900 joules. So there is a loss in kinetic energy of 900 joules. Okay, since the kinetic energy, total kinetic energy before impact is not equal to the total kinetic energy after impact, this is an inelastic collision. And what happened to this loss in kinetic energy? It is transferred to heat and sound. This lost energy will have been transferred into heat and sound, because during the impact, when the two objects collide, there is some heat produced and also there is a sound. Okay, so here a learning tip: remember that the idea of energy conservation, when considered in order to decide whether a collision is elastic or inelastic, only relates to the kinetic energy. Total energy in all forms must always be conserved. That is the law of conservation of energy. Energy cannot be created or destroyed, but it can be transferred from one form to another. So total energy is always conserved, but the kinetic energy is not conserved here. So if you consider 900 joules of energy is converted to heat and sound. So the total energy before that was 3900, total energy after is also 3900, which is this 3000 plus 900. Okay, but it's not the total kinetic energy. Here the total energy is the total kinetic energy, but after impact it is kinetic energy plus thermal energy plus sound energy. So that will equal 3900. Okay, then there are experiments for this. Now in unit 6, the experiments that are scattered throughout this chapter can be tested in unit 6 also. Okay, so here we can investigate elastic and inelastic collisions. Okay, let's go through this experiment. You can investigate elastic and inelastic collisions in the school lab if you cause head-on collisions and record the mass and velocity of each trolley. So you can find the momentum before collision and momentum after collision for each trolley. You can then calculate momentum at each stage. This should be conserved, because I told you before, momentum is always conserved. Now the kinetic energy may or may not be conserved, but momentum always, in any example, the momentum is conserved. You can also then calculate kinetic energy before and after the collision. So if you know the velocity and if you know the mass of the trolley, using the formula half mv squared, the formula for kinetic energy, you can find the kinetic energy of each trolley. Real cars are designed to absorb as much kinetic energy as possible when they crash. This reduces the energy available to cause injury to passengers. What is the best design on your experimental trolleys for a crumple zone to fulfill this idea of kinetic energy absorption? Now this is what I explained earlier over here. So what happens is, when the car collides, the front part of the car will crumple to absorb the energy. Otherwise what will happen? The energy will be transferred to the person and the person can get injured. Later on you will learn, when you learn about the force and change in momentum, you have the Newton's second law formula. The resultant force is change in momentum over time. Resultant force, in other words, is equal to rate of change of momentum. So if we can get the same change in momentum over a longer period of time, that will reduce the force. We will see the details afterwards. So what this crumple zone does is, it brings the car to a stop in a longer period of time, so that the car doesn't, the energy is not, a lot of energy is not transferred to the person and causes him injury. The force on the person is reduced due to the crumple zone, which crumples during the accident. Okay, so here we have more examples, but using the formula for kinetic energy and the formula for momentum, we can get a third formula, which is having the kinetic energy and the momentum. Now earlier you have learned only one formula for kinetic energy, which is what you have learned even in the IGCSE or O-level class. Kinetic energy equals half mv squared. But here we have kinetic energy is momentum squared divided by 2 times the mass. So how we get it is by substituting. Very simple. This is the formula that you had already learned about for kinetic energy. Then we have the momentum formula. Momentum is mass times velocity. So the velocity is momentum over mass. Then for V, we can substitute momentum over mass. Then we get this. So this square applies to both the P and the M, the momentum and the mass. And there is another M here. So what happens is, here it's M, here it's M squared. then you will get p squared divided by 2m, that is equal to the kinetic energy. So if you know the momentum and if you know the mass without knowing the velocity, you can still find the kinetic energy. Okay, let's go through another example. Now in the exam papers you can have momentum questions about subatomic particles like neutrons, electrons. Okay, here we have an example of something like that. Okay, so before collision and after collision. Okay, discovering mystery particles from their momentum and collisions. The explanation for this is already here. Okay, let's go through it. For example, if the detector registers an elastic collision with one of its neutrons, changing the neutron's velocity from stationary means at rest, the velocity is 0, to 3.4 into 10 to the power of 6 meters per second in a head-on collision with an unknown particle which was initially moving at 10% of the speed of light. Okay, the speed of light is 3 into 10 to the power of 8 meters per second. That is the speed that all the electromagnetic waves travel in air or in vacuum. Okay, and leaves the collision in the opposite direction 1.09 into 10 to the power of 3 meters per second. What is the mass of the mystery particle? The mass of a neutron is 1.67 into 10 to the power minus 27. When you get a question like this, to make it less complicated, okay, to help you understand it easy and for you to be able to solve it easily, the best thing is to draw a diagram. Okay, so here is the diagram before collision. Let's again look at the question and look at the diagram so that you have a better understanding of how to solve the question once you go through that. So always, whenever you can, draw a diagram so that the text becomes much easier for you to understand. Okay, so we have the neutron's velocity from stationary to 3.4 into 10 to the power 6 meters per second. See, in the beginning the neutron was stationary. Okay, I can zoom in here a bit so you can see it. The subscript is here. So this is for the neutron. Here mystery particle. So this is the initial velocity of the mystery particle. This is the final velocity of the mystery particle. Initial velocity of the neutron was 0, and then afterwards it is 3.4 into 10 to the power 6 meters per second. Alright, let's see over here, which was initially moving at 10% of the speed of light and leaves the collision in the opposite direction. Now the mystery particle already had a velocity which is 10% of the speed of light. The speed of light is 3 into 10 to the power 8 meters per second. 10% of that means you divide by 10. Okay, so 1/10. So in other words, 3 into 10 to the power 8 times 10 over 100 or 1 over 10. That is 3 into 10 to the power 7 meters per second. Then after collision, and leaves the collision in the opposite direction. So in the beginning, let's say this was moving to the right, and now after collision it moves at this speed in the opposite direction. That's why they have a minus sign. So if you consider to the right as positive, whatever is to the left will be negative. Okay, so we have what, 1.09 into 10 to the power 3, but the negative sign is used to indicate it is moving in the opposite direction. Okay, and they have also given us the mass of the neutron. We are supposed to find the mass of the mystery particle. Okay, so now you know all the quantities that they have given and what quantity you need to find. Now in your diagram, in addition to drawing this, you can also write here M and subscript mystery equals question mark, because that is what you need to find. You can also write over here mass of neutron, which they have already given, and you can write that 1.67 into 10 to the power minus 27 kilograms. Alright, so first we can find the momentum before collision. Total momentum before collision equals total momentum after collision. I told you in any case the total momentum before and total momentum after is the same, which means always the momentum is conserved. Over here the momentum of this before is 0 because it was stationary. Momentum is mass times velocity. Okay, so the total momentum is the momentum of the mystery particle. So momentum Total momentum is what? The momentum of the mystery particle plus the momentum of the neutron, but the momentum of the neutron is 0. So the total momentum is the momentum of the mystery particle, which is its mass times its initial velocity. So the mass of the mystery particle, which is what we need to find, times the initial velocity of the mystery particle, which is 3 into 10 to the power 7 meters per second. So this is total momentum before the collision or before the interaction. Okay, the best word we can use is interaction, not here when you say in general, because even in an explosion the energy is conserved, but in an explosion there is no collision. Okay, so that's why we use the word interaction. So total momentum before an interaction is equal to total momentum after the interaction. Interaction can be an explosion, it can be a collision, impact. Okay, it applies to all those. Alright, so after collision, so total momentum is what? Again, momentum of the mystery particle plus the momentum of the neutron. When you sum them together, you will get the total momentum after the collision. So that is what? Mass of the mystery particle times the velocity of the mystery particle. And momentum is a vector quantity, so you have to consider the direction. The momentum of the particle will be the same, will have the same direction as the velocity of the particle. Mass is a scalar quantity, so when you have momentum equals mass times velocity, when you multiply a scalar by a vector, the result is a vector. Like in F equals ma, in F equals ma, mass is a scalar, acceleration is a vector. So the resultant force and acceleration are both in the same direction. Okay, so that's what we have here. Mass times the velocity. Mass of the mystery particle we don't know, but the velocity of the mystery particle it's already given here, so we substitute over here, minus 1.09 into 10 to the power 3. Then mass of the neutron, that is already given in the question, 1.67 into 10 to the power minus 27 times the velocity of the neutron, that is the final velocity, because here we want the final momentum, which is 3.4 into 10 to the power 6. So it moves to the, let's say, to this in right, to the right. Then after impact, the mystery particle, which is what you have here in purple, that will move to the left. Okay, so we get another equation for this, and then total momentum before should be equal to total momentum after. Okay, so total momentum before is what we have here, this one. So we rewrite it here, and then it should be equal to this total momentum before. So we set them equal like this. You can see this same thing here is also here. Okay, so when you solve this equation, you will get this. You can try to work it out. Then you will get 1.89 into 10 to the power minus 28 kilograms. And keep in mind the negative sign here. This is approximately 207 times the mass of an electron. And so this can be identified as a particle called a muon. Later on you will learn about the different particles. Okay, under particle physics you will have this muon. You will learn what quarks are, what leptons are. Okay, then hadrons, muons. You will learn the details afterward, which is known to have this mass. Okay, so once you find this, you can see which one has 207 times the mass of an electron, and you can see it's a muon. Okay, I think we have arrived at the end of this page. Now it's very important that you memorize all these definitions, because in the exam paper they can ask you to define elastic collision, inelastic collision. So make sure you memorize this with understanding. You can write it in your own words, but the problem is if you miss a keyword, then you would not get the mark. For example, over here, an elastic collision is a collision in which total kinetic energy is conserved. It's not the kinetic energy of one particle before and after. That will be can be different after the collision. So it's the total kinetic energy. That means the kinetic energy of all the particles before collision should be equal to kinetic energy of all those particles after collision. That's what we mean by total kinetic energy is conserved. Conserved means what is before is the same as what is after. And if it's an inelastic collision, then it is not conserved. Okay, make sure you answer all these questions, because this is testing whether you understood all the theory. And if you have any difficulty answering these questions, you can review the theory, make sure you understand everything in the theory, and try to answer the questions. You should be able to answer them. but make sure you understand the theory very well, because all the past paper questions are based on the theory that you learn here. Okay, and the questions here are testing whether you understood what we learned just now. Okay, so that is 6.1 part 1, right? If you scroll up, you can see energy in collisions. Now 6.1 part 2, more collisions. By the end of this section, you should be able to apply the conservation of linear momentum to situations in 2 dimensions. So far you have seen momentum in 1 dimension where the object was moving in a straight line. Now we will see momentum in 2 dimensions where the object is moving in a plane. A good example is the example of a train moving in a straight railway track. So the train can move either forwards or backwards, that is along a straight line, that is 1 dimension. But if you take a car moving on a flat horizontal road, the car, in addition to moving forwards backwards in a straight line, it can also move sideways. So the car can move in a plane, that means it can move in 2 dimensions. The example of 3D is a helicopter. A helicopter can move forwards, backwards, sideways, as well as up and down. So a helicopter can move in 3 dimensions. But at this level we will learn only momentum in 1 dimension and 2 dimensions. But if you take higher levels of physics, you will learn momentum in 3 dimensions also. The university level you will learn it in 3 dimensions where you have I, J and K components of momentum. Analyze collisions in 2 dimensions. Calculate impulses and changes in momentum. Impulse. Okay, so we will see what that is. We have actually, this is the impulse. If you rearrange that equation for Newton's second law, F is equal to change in momentum over time. The resultant force is equal to change in momentum over time. And if you make the change in momentum the subject of that equation, now this is the Newton's second law equation. F equals ma. Acceleration, you can write it as v minus u over t. Then you get change in change in momentum over time, mv minus mu over t. And that's how you get this change in momentum over time. You move this term to the other, this quantity to the other side, and you get Ft is equal to delta P. The force times the time is equal to the change in momentum, and this is what we call the impulse. Calculate impulses and changes in momentum. Okay, so here is another experiment. Again, in unit 6 they can test you on this. So for each chapter, make sure you are familiar with the different experiments, because in unit 6 they can ask you experiments from these different chapters. Okay, so now it's about the impulse. Remember, impulse is the change in momentum. You can see that here. It is also force times the time. The force acts on a body for a certain period of time. That is what we have here, force times time. Say for example, a ball hits a bat. Okay, for example, in the game of cricket, let's say the ball strikes, the bat strikes the ball. Now the force on the ball exerted by the bat is exerted during the time the ball is in contact with the bat. So the time period there is delta t, which is the time the ball is in contact with the bat, because the bat exerts a force on the ball during the time it is in contact. Okay, so now you can understand what this delta t is. That is the time period during which the force is exerted on the other object. And when that happens, there is a change in momentum. For example, when the ball hits the bat, or when the bat hits the ball, the direction that the ball is moving changes. Also the speed of the ball can change. So therefore there is a change in the momentum. So the force caused the change in momentum of that ball. The force exerted by the bat on the ball caused the change in momentum of the ball. Okay, let's look at the experiment. In book 1, section 2.3.1, we saw how you can investigate the change in momentum over time for a trolley that is subject to a constant accelerating force. Now this is where we learned about F equals ma, the Newton's second law. We saw that if you increase the mass, then the acceleration can decrease, provided the resultant force is the same. F equals ma. So if you increase the mass, then the acceleration will decrease. Or if you keep the mass constant and if you increase the resultant force, the acceleration will increase. F equals ma. Okay, so this is referring to that experiment. constant accelerating force. Using the same apparatus, you can again record how different forces act over different time periods, cause the trolley to accelerate in different velocities. So you can same apparatus. From these results, you can calculate the impulse applied in each case. So the impulse is F times delta t, which is equal to delta p, the change in momentum, and the change in momentum is final momentum minus initial momentum. We use this Greek letter delta to indicate change. Okay, so delta means change in momentum. That means change in momentum means final momentum minus initial momentum. That's what we get a change. So if you want to find a change, what is that? Final minus initial will give you the change. Okay, this Greek letter capital delta is used to indicate change. A graph of impulse on the y-axis against change in velocity on the x-axis should give a straight best fit line through the origin. Okay, so we have impulse. So you can think of that I. So it's a graph of I versus V, because the mass is constant. The gradient. Okay, so if you it's in the form y equals mx. Okay, we can actually write it down and have a look. Okay, so we can write it down like this. On the y-axis, we have the impulse. You can see they mentioned that here, against change in velocity on the x-axis. So we can write this I equals delta mv like this, because the mass of the object is constant. We are not changing the mass of the object, but the velocity of the object changes. So we can write I equals m times delta v, and if you read the explanation here, they say delta v on the x-axis. Okay, so we have y equals mx. This is on the x-axis, this is on the y-axis. Then the gradient will be m, the mass. Now if you plot a graph of I versus delta v, now again it's not v, it's delta v, the change in velocity, then the gradient will be the mass. So the gradient of this graph will be the mass, and they mention it here. The straight line verifies the impulse equation, and the gradient of it will give the mass of the accelerating trolley and its weights. Make sure you have a good understanding of this practical, as your understanding of the experimental method may be assessed in your examinations. This is what I mentioned in unit 6. They can test you on this. So not only this, if they give you a graph and if they tell you to plot a graph of, let's say, I versus delta v or something, then you can put it in the form y equals mx plus c. Now again, there is no plus c part here. So the y-intercept is 0. That's why it passes through the origin. And you can see it's in the form y equals mx, which means it has to be a straight line passing through the origin. It's a directly proportional relationship. I is directly proportional to delta v. Okay, so again you can see the equation impulse. The unit of impulse is Newton seconds. We can also write this in SI base units, because the impulse is change in momentum. Momentum has the unit kilogram meters per second. Unit of mass is kilogram, unit of velocity is meters per second. So if you write this in SI base units, it will be kilogram meters per second. You have learned that there are about 7. You have learned about 7 SI base units. Okay, kilogram is a base unit, meter is a base unit, second is a base unit. All the base units are SI units, but not all the SI units are base units. Newton is a SI unit, but it is not a base unit. Now, how do we get this unit Newton second? Because force is in newtons, time is in seconds, therefore the impulse will have the unit Newton seconds. And it is the same unit as kilogram meters per second. Change in momentum has this unit. So this equation is very important. You have to remember this equation. And how we get this? From the Newton second law equation, F equals ma. You can try to work it out. If you use F equals ma and substitute for acceleration v minus u over t, you will get F equals m in brackets v minus u over 2. So it will be mv minus mu over t. mv is final momentum, mu is initial momentum. So it's final momentum minus initial momentum, which is the change in momentum over time. Okay, let's go through the example so that you can understand this better. The examples are here so that you understood the theory better. What is the impulse needed to accelerate a 1000 kilogram car from rest to 25 meters per second? Again, in a question like this, the quantities that they have given you, you can write them separately. For example, mass equals 1000 kilograms. From rest means the initial velocity is 0, u is 0. Then final velocity is 25. If you write it like that, then again it becomes easier for you to understand and solve the question. And what you are supposed to find is the impulse. So capital I equals, you can put a question mark. Okay, so impulse is what they are asking. Now you have learned the one equation for impulse, that is impulse is force times delta t, or change in momentum. So using this equation you can see what you need to find, that is the momentum. Okay, so impulse, there are two actually. Impulse is equal to force times time. So we have two equations for impulse. Impulse is what? Force times time, or change in momentum. Alright, so the initial momentum is 0. So mu is 0, the final momentum is 25. So we are not writing that term of initial momentum because it's 0. So change in momentum is final momentum mv minus initial momentum mu. Mu is 0, final momentum is m, that is 1000, times v, that is 25. Okay, so the change in momentum is 25,000 kilogram meters per second, or we can say the impulse is 25,000 kilogram meters per second, or 25,000 newtons per Newton seconds. Newton second is also a unit of moment. If the car needed to stop in 3.8 seconds, what force would the brakes need to apply? They have given the time, and they are telling for it to stop. That means the final velocity is 0 and it needs to stop in this period of time. They are asking the force. So again, the equation that has these quantities is Ft equals m delta v. M delta v is the change in momentum. Ft is the force times time, which is impulse. So impulse is equal to this. Also it's equal to this. Now first we already found the change in momentum. That is again 25,000, which is the same as before because it was at rest and then it accelerated until it reached this speed. So now it's going from this speed again to 0. So again the change in momentum is the same. But so it doesn't depend on the time. It is independent of the time. It's just the change in momentum just depends on the mass and the initial momentum, and mass and the final momentum. Okay, so we know this, and now we are given the time. The time is 3.8 seconds. So we get 6,600 newtons to two significant figures. That means a force of 6,600 newtons is required to bring the car from to rest from a speed of 25 meters per second if it has a mass of 1000 kilograms. Okay, so make sure you understand the question. Again, about significant figures, if you are not familiar, I have uploaded 2 videos explaining everything you need to know about significant figures. You can watch those videos. Okay, so in those videos I'm explaining how to identify the number of significant figures in a number, how to do significant figure operations, and I have also solved several example questions there. Okay, I'm explaining how to solve certain questions on significant figures. Make sure you go through those videos so you have a good understanding about significant figures. Okay, in this question we are supposed to calculate the velocity of the rocket after the collision, and everything that is mentioned here is shown in the diagram except for the masses. In this diagram you can also show the mass of the rocket 350, mass of the meteoroid 20 kilograms, and you are supposed to find the velocity of the rocket after the collision. So what happens is, once this meteoroid collides with this, you can see it embeds itself into it. That means it sticks to the rocket. It is inside the rocket. So both move together as one body. Okay, when you are drawing these diagrams, you don't need to draw it like this. You can just draw circle, one circle for the rocket, another circle for the meteoroid, and also you can see a meteoroid traveling at 15 meters per second. You see it's indicated in the diagram, comes from behind at an angle of 45 degrees to the line of movement of the rocket. This is the line of movement. Again, this is very important. And then you can see this, if you see the angle here, it is 45 degrees. So because this line is parallel to this direction, then this angle is also 45 because they are alternate angles. Okay, so what we can do is, this is in 2 dimensions. We can resolve the velocities in the vertical, in the x direction and the y direction, and then find the total momentum in the horizontal, that is x direction, and total momentum in the y direction, before and after, and always it should be the same. So total momentum before impact should be the same as after impact in both the x and y direction. So if you consider the x direction separately, the total momentum in the x direction before impact should be equal to the total momentum of the body after interaction in the x direction, after collision in the x direction. Same way, total momentum before impact in the y direction should be equal to total momentum after impact or after interaction in the y direction. Okay, so that's what we are going to do. First, we can resolve the momentum in the x and y directions separately, and you know the mass is the same, so the momentum depends on the velocity. That means we have to resolve the velocity in the vertical and horizontal direction separately. Now over here it is moving in the horizontal direction, so it has no effect in the vertical direction. In the vertical direction, the momentum of the rocket is 0 because the velocity of the rocket in the vertical direction is 0. No component in the vertical direction. But here we will have components in both the horizontal and vertical directions. So how you find the momentum, the velocity in the horizontal direction is 15 cosine 45. If it's sweeping the angle, now when you are finding the component in this direction, it's 15. You have to go this way. So it's like sweeping the angle. 15 cosine 45 will be this. And this way it is 15 sine 45. But cosine 45 is equal to sine 45. You see this angle is 90 degrees. So here also the angle is 45. So cosine 45 is equal to sine 45 degrees. Okay, so this is what we are finding. 15 cosine 45 before collision parallel to the rocket motion, that is in this direction. You know, we don't know whether it's horizontal, vertical. So that's why they say parallel to rocket motion. But if you look at this diagram, you can think this is the x direction, this is the y direction, this is the horizontal direction, this is the vertical direction. But we don't know. So that's why they say parallel to rocket motion. So that means in the x direction, as you can see in this diagram. So it will be 15 cosine 45, that is 10.6. You can use your calculator. Make sure your calculator is in degree mode if you are entering the value in degrees. If you are entering the angle in radians, your calculator has to be in radian mode. Then the momentum of the meteor is 20 times 10.6. So it's the mass. Okay, mass times the velocity, component of velocity in the parallel direction. That will give the momentum in the parallel direction. Now this is the momentum of the meteoroid before interaction or before impact, before collision. Same way we can find for the rocket. It's very simple. So it's 350 times 8. Okay, so nothing to resolve here because it's in this direction, parallel to the direction of the rocket. So we get the total momentum is the momentum of the meteor plus the momentum of the rocket, and this is the total momentum in the parallel direction to the direction the rocket is moving. 3012 kilogram meters per second. Now we find perpendicular to rocket motion, that is in the y direction. Now this has no value, so that's why we say 0. 350 is the mass of the rocket, but it has no component in the vertical direction. If you do 8 cosine 90, it's 0. So that's why the momentum of the rocket in the y direction before impact is 0. But the momentum of the meteoroid is again 10.6 because sine 45 is cosine equal to cosine 45. You get again the same value, 212. Then the total momentum before impact in the y direction is the sum of these two, which is 212 kilogram meters per second. Okay, so this is the momentum, total momentum in the x and y directions respectively, that is parallel to the rocket's initial motion and perpendicular to its initial motion. Okay, so we can draw a vector diagram. So vector sum of momenta, the plural of momentum is momenta. 212 in this direction, 3012 in this direction. Okay, so we can find the resultant momentum. Okay, so vector sum of momenta in 2 dimensions. So we get now again you can use Pythagoras theorem here. Okay, vectors are equal if they have the same direction and the same size. The size of a vector is indicated by the length of the arrow. The direction of the vector is indicated by the direction of the arrow. And like I mentioned before, two vectors are equal if they have the same magnitude and direction. Okay, so you can imagine this arrow, we can also move it here, but the direction has to remain the same, the length has to remain the same. Okay, so you can see we have a vector triangle, then we can get the resultant like this. Okay, we can use Pythagoras theorem. So this plus this, when you move this here you have this plus this by vector addition is equal to that. Okay, so we use Pythagoras theorem and then we get the size of the total momentum. Okay, that is this much, 3019 kilogram meters per second. We can also find the angle, this angle here, because momentum is a vector quantity. Then using tan we can find that this side, that is 212, opposite over adjacent divided by 3012, arctan of that value 4 degrees. So the angle here is 4 degrees. Now make sure your answer makes sense. It has to be about 4 degrees. Why? Because this side is 3012 but this side is only 212. So the resultant moment is more towards this side rather than this direction. That's why here the angle is 4 degrees, because this number is much larger compared to this. So that means the resultant should be more closer to this direction than to this direction. Okay, so then we get the total momentum after impact should be equal to total momentum before impact. I told you before, always the momentum is conserved in any collision or any interaction. Total momentum before is always equal to total momentum after. So that's what we have here. This is the total momentum. Now this was what we found before impact. After impact also it should be the same. So that's why here they are using V after. Okay, so if you move this to this side, then it's mass times velocity plus mass times velocity, but both have the same velocity after impact because the meteor got embedded in the rocket. So it's moving like one body. Do you understand? That's why we can sum the two bodies here. So the total mass times the final velocity will give you the total momentum. Why we can use it like this? Because the two bodies are moving together. The meteor embedded itself inside in the rocket. It embedded in the rocket. So they are moving together. So we can use it like this. Now total momentum before equals total momentum after. So we can use 3019 here for total momentum after impact. Then the mass of the rocket plus the mass of the meteor, 350 plus 20, which is 370. You get 8.16. Okay, 8.16, and already we found the direction. So the spacecraft with embedded meteorite carries on at 8.16 meters per second at an angle 4 degrees of the original direction of motion, because this was the original direction of motion of the rocket. So after the meteor collides with it, it moves in that direction with the meteor together. Okay, so that was one example. Now we have another one here, and after that we are done with the chapter. So let's go through the second example to help you understand this better. Now again, if we just review what we learned, we resolve in the horizontal and vertical directions, and then we get the resultant of those two. Okay, so what happens in the end, that is after collision, we find by the resultant, and after that we can also find the angle, and that way we can get the answer. Very simple. Okay, so there is another example here, deep space collision, and they have also given us a diagram. Let's see where this question starts. Okay, it starts somewhere here. Okay, let's discuss this example. So what happens is, there is an asteroid that is coming towards the Earth, and they predict that it would strike the Earth in 2035, 2036 or 2037. Now what we can do is, they say we can crash a spacecraft onto this so that it will change the direction of this asteroid and prevent it from striking the Earth. So they have the spacecraft which is moving at 6 kilometers per second. Now this is traveling at 12 kilometers per second. The mass of this asteroid is 6.1 into 10 to the power 10 kilograms. And the mass of the impactor craft, that is this one, is 4,000 kilograms. It has cleared the collision if this impact collided with Apophis, that is the asteroid, at right angles, we can calculate the change in angle of the asteroid. So let's do that now. In the beginning this is moving this way, and this is the craft, it's moving that way. Then they collide. So after collision, both will move together, we can say, and we are supposed to find the direction. So this is similar to the previous question. Could we hit an asteroid hard enough to save Earth from asteroid impact hazards before collision? Now again, this is very similar to the previous one. So we can find the momentum in the horizontal and vertical directions, or we can say direction parallel to the asteroid and perpendicular to the asteroid. Now this is traveling in the direction perpendicular to the asteroid. So momentum of asteroid, here we have momentum of impactor craft, that is mass times the velocity, initial momentum, that is before collision. The mass is 6.1 into 10 to the power 10, and the velocity is 12.6 into 10 to the power 3 meters per second, because this is in kilometers. So you get the momentum of the asteroid before the collision, and this is in the horizontal direction, as you can see in the diagram. Then the momentum of the asteroid, that is this much, but this is in the vertical direction. So mass is 4000 kilograms, that is the same as 4 into 10 to the power 3 kilograms, and the velocity is 6 kilometers per second. Okay, 6 into 10 to the power 3 meters per second. So we get the answer in kilogram meters per second, because we didn't convert the we have it in kilograms. Here we converted it from kilometers to meters. So we get kilograms meters per second, kilogram meters per second. But remember, this is in the horizontal direction, as you can see in the diagram. This is in the vertical direction. Now very easy, find the total momentum after impact. So again, you can have a vector diagram like this, 7.69 into 10 to the power 14 meters per second this way, and for this it is 2.4 into 10 to the power 7. You can use the vector triangle and find this one. So use Pythagoras theorem to find this side, and that will be the momentum after impact. Both moving, we assume both move together, and again you can use tan to find the angle that it moves after impact. The momentum of the combined object after the impactor embeds in the asteroid is the vector sum of the two initial momenta, which are at right angles to each other. So you see Pythagoras theorem used, 7.69 into 10 to the power 14, which is what you have here, and then this also 2.4 into 10 to the power 7 square, and then Pythagoras theorem, you get this is the momentum after impact of the combined object, that is both are moving together. This embeds itself or sticks to this. They can use the word embed, coalesce, sticks together, all mean the same thing. Okay, so after you find this, now you know the momentum before impact, that is this one, that is equal to the momentum after impact. So sorry, this is the momentum after impact. Okay, so you have that, and the velocity after impact times the mass after impact. Mass is the total mass, that is this one, so you can find the velocity. Okay, both are moving together, so they have the same velocity. The mass, you can consider it as one body, which is the sum of the individual masses. Then you get 12.6 kilometers per second. Okay, you saw, if you go through this before, also 12.6, after also 12.6, that is because we round it off to 3 significant figures. So it's a very small change, but when you round it off to 3 significant figures, it's still the same, because this is much heavier compared to this object. And also yeah, so that's why there isn't a big change, but even a small change in the angle can significantly deviate it once it comes towards the earth. So let's say it's a very small, maybe 0.001 degrees, but this is much further from the earth. So once it comes towards the earth, you can see it's much further away from the earth. Okay, so a small change in the angle will deviate it, so that once it comes close to the earth, so this deviation occurs much further away. So once it comes close to the earth, it doesn't hit the earth. Alright, so let's find the angle. Now again we use tan. Tan is opposite over adjacent. This side divided by this side, 2.4 into 10 to the power 7 divided by 7.69 into 10 to the power 14. You get this. This is the angle. You can see 1.79 into 10 to the power minus 6 degrees. Such a small angle. Although less than 2 micro degrees sounds like an insignificantly small angle, this would represent a change in position of nearly 30 kilometers as Apophis crosses the Earth's orbit from one side of the Sun to the other. So you see 30 kilometer difference. This might be just enough to avert a collision with Earth that would have 100 times more energy than all the explosives used in Second World War. So that is, if it collides, this is how much energy it would release. Alright, so here is another experiment investigating 2D collisions. Okay, so here another experiment. You can investigate two-dimensional collisions in the school lab. We saw in book 1 section 2.1.2 that by analyzing video footage of an object's movement frame by frame, we can calculate any changes in velocity. So when we view frame by frame, that is for equal time intervals. We see the different positions of the object. So if the distance between the images is increasing, that means the ball is accelerating, the object is accelerating. If it's decreasing, it's decelerating. If the distance between the images is the same, that means it's moving with constant velocity. So when we view frame by frame, it is for equal time intervals that we see it. We can calculate any changes in velocity with measurement scales in 2 dimensions. The components of the velocity in each dimension can be isolated. Thus, separate calculations can be made in each dimension. In order to verify the conservation of momentum in 2 dimensions, make sure you have a good understanding of this practical as your understanding of the experimental method may be assessed in your examinations. Okay. So again, using this, we can find the velocity, and once we know the velocity, the mass we can measure by using a top band balance or electronic balance. So we can find the momentum. So that's what they are saying here. Okay. So we have arrived at the end of the chapter 6. Make sure you answer all these questions, because this will make sure that you really understood the theory. Make sure you answer them and check the answers. The answers come separately. You can download it from the internet. Make sure you get them correct. If you have any problem answering these questions, go back and review the theory, because it is based on what you learned here. So you go back, review the theory, because the questions here are based on what you learned here and in the previous part. It is based only on this chapter. So just only this bit only you will have to review to answer the questions. Answer the questions, check the answers at the back. Again, the definitions are important. In the exam paper, they can ask you to define the impulse. So whatever you see here in red, key definitions, memorize it with understanding. You can try to write in your own words, but if you miss a certain keyword, you won't get the mark. So that's why we say memorize it with understanding. The impulse is a force acting for a certain time, causing a change in the object's momentum. Impulse is force times time. This is the resultant force. Okay, so that's the end of chapter 6. So after you finish answering those questions which are scattered throughout the chapter, you can start answering these end of chapter questions, which are called exam style questions. Do all this, then check the answers again for all this, and that is the end of chapter 6.1.